And for those who did not come to the class but watch the video, what we are teaching today are very critical. It's not about memorizing the theorem, but all the skill we are going to use today. You need to, we are going to have a final discussion or important discussion on how to read a quantum circuit, how to do matrix multiplication, and all those bracket notation, right? So although the first thing I'm going to talk about is called no cloning theorem. This looks like nothing to learn, right? The conclusion is that you cannot copy any states, any quantum states at will. Only a few states which are the basis state that you can copy. But for any arbitrary states, you cannot copy. Done, right? If you agree with that, right? For this part. But the point is, in this process, we're going to practice many important skills in derivation and confirm our understanding of some important quantum computing concept. Okay. Okay. So what is the purpose? So I'm going to disprove this. This theorem, this thing. The point is that if a quantum state, right? Again, what is a quantum state? It's a vector, right? Can be cloned or a copy, right? Then let's assume that we can copy an arbitrary quantum state, okay? Then there exists an operator, right? Because if you want to copy something, you should have an operation, okay? Such that psi 0 after this operation becomes psi. So let's understand this a little bit. Again, each cat is a state. How many qubits do we have here? When some say 2, it can be 2, but I did not say anything, right? So besides 2, how many can we have? Any qubit, yes. Right? I just say psi. So you can say you did not give me complete information. Right? That is what you can say. So here I assume actually it is an n qubit state. So this psi can be 2, can be 1 in your first case, right? Can be 2, can be 3, can be 4. And I have another n qubit, right? So basically my goal is that I have this n qubit, 2 n qubits, right? The first n qubit contains the state that I want, right? How many bases do I have for n qubits? 2 to the power n, right? So doesn't matter, it's just a review, right? So now I also have another n qubit. When I say copy, isn't that I am going to copy this psi from this n qubit to another n qubit? And after I copy them, both of them are psi. Make sense? For example, if n is equal to 1, I might be talking about this. I have a alpha 0 plus beta 1, 0. How many qubits do I have here? 2, right? After the operation, how should it look like after the operation? Alpha 0 plus beta 1, tensor product of 0 plus beta 1. Does it make sense to you? On what I mean by copying? Right? So this one may be the spin of an electron. This is the spin of another electron. At the beginning, this electron, the first electron has a certain superposition, right? 0 can be spin up, 1 is spin down, alpha 0 plus beta. If it's on broad sphere, it's pointing a certain location. Another electron is spin up. After the operation, if I say I successfully copy the information from this electron to another electron, then both of them should be alpha 0 plus beta 1. Make sense? And of course, this is 1 qubit. If I have n qubit, of course, you can have just tensor product of many, a general state, right? And then you copy to another n qubit. That's the meaning of copying. It doesn't have to be 0, but we start with 0 because if we can show that I can copy to 0 for any state, I can always just let it cool down to ground state, right? So I can still copy from one register to another register. So this is just for convenience. Make sense? Okay, so if this is possible, right, then what I'm going to do is I'm going to prove by contradiction. By contradiction, if you remember, I assume this is true. Then I'm going to derive something eventually to tell you that something contradicts each other if you base on this. For example, eventually I will say 0 equal to 1. Then you know 0 is not equal to 1. Then the assumption is incorrect. Okay, so proof by contradiction. So if this is the case, let's say I have a state which is A. Again, the original state, I call it A. It's just another notation for psi, right? Just A. After copying, what do I get? AA. Very good. Okay, if I have a state which is B, after applying this operation, what do I get? BB, right? Okay, then also, if I have a state that is phi equals to 1 over square root 2 A plus B, for example, I have a state that is phi, right? Just a superposition. Then what happens if I apply the copying action to it? What do I get? By definition, just simplify. No need to spell it out yet. 5. Yeah. And then I will go to what you just said. Equals to what? 1/2 square root, right? A plus B tensor product 1 over square root A plus B. Correct? So after copying, I should get 1/2 AA plus AB plus BA plus BB. Is this okay? Now just recall, right? Because A and B can be 0 or 1, or it can be even another general state, right? But do you understand what's the meaning of AB in the bracket, in the cat? It is equivalent to what? Maybe you don't know my questions, but it is just A tensor product B, right? Remember, just want to remind you about our notation. This is nothing but just A tensor product B. And if we are lazy, we can write it in this way. And even more simplified, it will be just AB, right? Let's remember all this basic thing, right? So this operation tells us that after copying, I will get this, right? Okay. Now, however, we also know that if I look at psi 0 in this way. This is just equal to 1 over square root 2 A plus B, 0. Correct? I substitute first. So then I continue. This is just over equal to A 0 plus B 0. Do you agree? Just distribution rule, right? And again, this is tensor product. You should be very familiar with this. You should know that this one means the first qubit, tensor product with the second qubit. And I can do the distribution so that it will be A tensor product 0 plus B tensor product 0. Is that okay? Now, if I look at this, then I say I want to apply the copying action. Now, the copying action is supposed to be linear, right? Because this is a linear system. What do you get if you try to do it based on this? Then I do it one by one. What is A0 after copying? AA. What is B0 after copying? BB. But I'm copying the same thing. I was copying psi 0 and psi 0. But these two are not the same. I expect them to be the same, right? But they are not the same. So this proves that it's contradictory. And that's why the assumption is wrong. And so this mathematical trait really doesn't matter if you can derive it again, but the point is you need to understand every step. So any questions? Right? Sorry, can you say again the question?
Separate. Do you consider those a clone of each other or not? At the same probability.
You mean that you try to apply A0 to Hadamard to A0? Uh-huh. Yeah. Uh, why would you say, are you trying to say that I have A0 and then you apply identity to the first one and Hadamard to the second one? Yeah. And by the way, this is a good exercise, right? Review. You have 0, 0, and then, sorry, Hadamard to the first. And then the second one will be identity. No, we are not cloning, right? Because well, we need to put a. I mean, 0, 0 is already identical. You don't need to do anything. They're identical already, right? Cloning is saying that can you copy the state of the first qubit to the second qubit for a general state? Yeah. If it's so, this one did not go deep, right? This is only correct. Actually, here Yeah, I think I'm missing the. Three, four. Yeah, so cloning is that you need to copy. Do I answer your question? Yeah. Okay, any questions? Yeah. Yeah, quantum teleportation. Mm-hmm. Right. So we'll discuss quantum teleportation later, but basically in quantum teleportation is that you will, looks like copy, you transfer the state of this qubit from here to a qubit far away, but doesn't need to be far away, it can be just next to you, right? But in that process, your original state got destroyed. So there's no copying action. So when we say cloning, we try to say that you need to keep the original one. If you go through the quantum teleportation algorithm, you will find that the first qubit will get destroyed because you need to do measurement. Yeah, so that's a good question. And that is another reason why we cannot copy. Okay, so this slide is skip. I don't want to go to too much detail. Okay, so we cannot copy by reading also, right? Here I try to be. I don't know why I have this slide. Okay. So I just want to remind you, you also can say, when you try to read it and then copy, you actually will collapse it to a basis state. So this is like quantum teleportation, right? But of course, that's not quantum teleportation, but just like within quantum teleportation, you need to do measurement. You destroy the original qubit. So this is even worse. We're not talking about teleportation. It's just that you just cannot get anything by measurement and then repeat, right? Because if you know the state of a qubit exactly, you always can prepare another one. Then this is copying, cloning, right? But the problem is that in quantum computing or quantum mechanics, once you do measurement, it will collapse to the basis state. So you are going to destroy the original copy. You won't be able to clone. Okay? Good. I have some problem with my numbers. Okay. So now I want to give you an example. This is kind of the first quantum circuit we will learn, right? But we will just learn the basics. So it means in the midterm, it won't be very complicated. But however, it will be as difficult as this one. So let's go back to our assignment 1. In assignment 1, we talk about the Bell states, right? So what is, for when I say C4, C to the power 4, how many qubits do we have? 2. Very good. Because this is C to the power 2 to the power 2. This is n equal to 2. 2-qubit system. Okay. So in a 2-qubit system or C4, how many basis states do we have? Yeah, I know it's trivial, right? But you need to be very confident in answering my question. So if this is the case, we can have this one, I call it the standard basis or trivial one, right? Why? Because naturally you would say U1 is 1 0 0 0, U2 is 0 1 0 0, U3 is 0 0 1 0, and U4 is 0 0 0 1, right? Are they orthonormal? Yes, right? Because the inner product is 0 and their length is 1, right? I mean, inner product between each of them is 0. But we can also have a Bell state, which we learned in assignment 1, right? At that time, you don't know is significant. So the first one, we call it phi plus capital equal to 1 over square root 2, 1001. Okay, phi minus equal to 1 over square root 2, 100 negative 1. Psi plus equals to 1 over square root 2, 0, 0, 1, 1, 0, right? And then psi minus equal to 1 over square root 2, 0, 1, negative 1, 0. Okay, are they normalized vector? Yes, right? Because I have two components for each, and each of them has a magnitude of 1 over square root 2. Right? And are they orthogonal to each other? Yes, right? You did not try to calculate, but you did that in assignment 1, right? If you say no, then I'm going to take back your point. Okay, good. But now I have a question to you. When I write this as 1001, what is the basis that I'm using? Right? Whenever you write something in matrix form, you need to talk about which coordinates you are using, which basis you are using. So which basis are we using when I write 1001? Yeah, it's talking the standard basis. Right? So we can say this is, there are a few ways to do this. We can, how about here? This is, you can say this is 0, 0, right? But what is the meaning of 0, 0 here? It is U1. Okay, this is U1. I did not put in, maybe I should put in bracket notation, but it's the same, right? U1 equals to 0, 0. Right, because there is the standard basis. How do I obtain this, by the way, from two single qubit? How do I get this basis state? I just do tensor products of the single qubit basis state, right? So this is a review, right? Maybe you think I'm talking too much, but for example, this one is just equal to 0, 1, tensor product 0, 1, correct? And how do you do tensor products? You put, just multiply each, right? Do the permutation. 0 times 0, 0 times 1, 1 times 0, 1 times 1, you get 0, 0, 0, 1. Right? And that's why this is called 1, 1, right? This is just 1, 1. Right? So I recognize that, right? Maybe it doesn't hurt to do more because we're going to do midterm. Just to remind you, what is this guy? Psi minus is nothing but just 1 over square root 2, 0, 0. No. 0, I don't have 0, 0, right? I only have 0, 1, minus 1, 0, and I don't have 1, 1. Correct? Because these components refer to 0, 1. These components refer to 1, 0. This component refer to 1, 1. And of course, the so-called 0, 0 is U1, 0, 1 is U2, 1, 0 is U3, 1, 1 is U4. So we will write down the matrix form. We basically are working in the basis, standard basis. Any questions? Again, it's just a review. Right, so the question here is that how do I transform? I think the point is I just want to show you the quantum circuits, right? So to, right, convert which basis is that actually? Right, for example, to convert the standard basis, instead of basis, I just convert standard basis vectors, right, to Bell state basis vectors. Right, I can use this circuit. Okay, so this is an important part. You will see something like this in midterm. You need to understand this very well. So maybe let me use circle. Sometimes we use circle, sometimes we use X. So this is input. This is output. And let me tell you, this is LSB. In this particular circuit, this is MSB. First of all, to read this circuit, first of all, the input comes from the left. The output goes at the right. Okay? So LSB is what? The least significant figure. It is the one on the left or right when we write the bracket. Just think about when you write a decimal number, right? 102. Which one is the least significant? 2. Yeah? Because if I owe you $1,002, you don't care about if I give you $2, you care if I give you that 1,000, right? So the 1 is more significant than 2, right? Think it this way. So LSB is on the right. For our convention, with what we call the little endian. Okay? So it basically saying that the lower quantum qubit register, right? Because it's just this 9 represent register will be the LSB and the top will be the MSB. This is opposite to what you did in assignment 2. Okay? But anyway, let's understand it. It goes through 2 gates. What are these gates? What is this H? Hadamard gate. What is I? Identity means nothing happened, right? What is this gate? Control NOT, right? So in terms of symbol, I think I am not consistent. Okay, this is control NOT, right? Okay, good. Now, however, if I want to use the IBM convention, I'm going to draw the MSB at the bottom. Right? So you need to pay attention when I give you the circuit. Where is the MSB? So if I draw in the circuit, this is equivalent to this. Now this is the MSB. And this is the LSB. Make sense? And I did not do anything but just flip my screen upside down. That's it. So looks like I make this a big deal, right? But there's nothing new. I just flip it. Okay. So the input go from left to right in the circuits. But what is the equation or the gates correspond to this? If I want to apply it to a state, let's say a general state A, what happened? How should I apply it if I want to write a matrix where A is just a vector column, right? Column vector, right? So I need to apply a matrix to it. What should I apply to it first? Thank you. I and Hadamard gate, right? But I is applied to what? LSB. So I would write I here and then Hadamard gate on the left. Make sense? Because H is applied to MSB. It's the same for both circuits. And I have this H tensor product I. And then what do I apply? Just imagine you are the quantum signal. Now you go through here. Yes, I got I got H. And then what do I receive? I got control NOT, right? So this is, I just write it as U exclusive OR. Is that okay? So maybe let me rewrite this instead of A. I call this input cat. And this will give me the output cat. right? So this is the equation correspond to this circuit. Do you agree? Now, I want to warn you, be very careful. You probably don't have this problem, but still someone may make mistake. In the circuit, you see the input go from left to right. So that's why it will first fill the gates on the left and then the gates on the right. But when you write equation, because it fill the gates on the left, that's why you need to put the gates to the right, the symbol to the right, right? So it just swap, right? This one is H and then control NOT. But here you have control NOT and then H. And the only reason, just because when we do multiplication, we go from right to left. Right? We are showing that this input will receive this matrix first, because every matrix is a gate. And then you will receive this matrix. So you should be careful about this, right? Because some people careless, and then they might write input, and then control NOT, and then H extensor I. That would be completely wrong, because you swap the position of the two gates. Is this warning clear to you? Do you understand what I'm talking about? Any questions? I mean, if this is clear, the rest is just math. So let's look at this. I say that this whole quantum circuit is just exclusive or H tensor product I. Okay? I would like you to remember what they are, but I usually will give you in the exam, but don't take it for granted. I might not. The exclusive OR is given as 1 0 0 0 0 1 0 0 0 0 0 1 0 0 1 0. And this is only true if the control qubit is the MSB. Do you see that in our circuits, MSB has dot, right? And the one that receives the NOT operation is the LSB. So you need to be careful whether the control qubit is MSB or LSB. Okay, I'm going to show you the control NOT gate when the control NOT gate matrix when the control qubit is LSB. Does it matter if I swap this? It matters, because he asked, can I do I tensor product H? It just basically saying, can I swap this quantum gate with H at the bottom and I at the top? They are different, right? So when we write this one, we put the MSB on the left and MSB on the right. So let's see why. Because you can see clearly from the matrix multiplication. So first of all, control NOT is 1 0 0 0 0 1 0 0 0 0 0 1 0 0 1 0, right? And what is H? 1 over square root 2. Anyone remember? 1, yeah? -1, yes. And then we tensor product I. What is I? 1 0 0 1, right? So how do we do the tensor product? Let me just keep writing. This is control NOT, right? I hope you can memorize now. I write it so many times. It's just diagonal, but then you swap the second, the third and fourth row. This is equals to 1 over square root 2, 1 times 1 0 0 1, right? I try to have an intermediate step, but which is incorrect mathematically, I think. I don't know. But yeah, that's how I do it. Make sense? And I can also take the square roots out. I continue to write the control NOT gate. And then I just multiply it. The first one is 1, 1 0 0 1, again 1, 1 0 0 1, 1, 1 0 0 1, but -1, -1 0 0, -1. right? So tensor product, you need to be very familiar with that. And if I give you a quantum circuit, you should be able to find the matrix form. So what is this? 1 over square root 2. Now you can see that it's nothing but just this row times this column give me the first element. This row times this column give me the second element. This row times this column, this row times this column, right? And I only have the first one that is 1. The other, a 0, means they have no effect. It's just like a filter. Exactly if you did a image processing in the old time, now they all use machine learning, but image processing in the old time, this is just a filter. That's matrix, right? So this 1 times that. So basically, the first row, you just take this guy. Okay? So if you do that, you get 1, 0, 1, 0. Same for the second row. You have a filter, which is 1 here. If you don't know the filter concept, you just multiply it. Again, you see the second one has 1. So 0, 1, 0, 1. How about the third one? When I multiply third row, multiply this, what do I get? I get the fourth row. Very good, because only the fourth element is 1, right? The rest is 0. So basically, I'm just copying the fourth row to the third row, right? And how about the fourth one? I have the 1 on the third location, right? So if I multiply this by this one, I'm actually copying the third row, right? That's why I get 1, 0, negative 1, 0. Let me check if this is correct. Okay, so by the way, what is this? This is a matrix, right? Can I call this a quantum gate? Very good. It needs to be unitary, but because everything is unitary, after you multiply them, they are still unitary. Correct? It needs to be unitary. And you see it is, because one way to check unitary is look at every column are orthonormal, right? And you see they are orthonormal. It is a quantum gate. Then what? Then what are you talking about? We have so many quantum gates, it's still a quantum gate. And it's true. I mean, a whole quantum circuit is just a big quantum gate, right? You just combine them together. And if you were able to implement this quantum gate directly, you are done. But the fidelity is very low, right? And that's why we will do this decomposition. If you are 100 qubit, you decompose to many 2 qubit and 1 qubit gate, and you have very deep circuit, it's true. But if you want to implement a 100 by 100 qubit gate, it's almost impossible. You need to engineer all the laser pulse, very complex, right? And it's not general. But yes, after all, a quantum circuit is just a quantum gate, because a quantum gate is to rotate a state on the rotate a state in the hyperspace. If you have multiple qubit, you cannot see it, but it's still rotation, just like the Broad sphere for 1 qubit. So yeah, you keep rotating at different angle, and eventually it's just one effective rotation after all, correct? When you have a whole quantum circuit. So it's a quantum gate. Okay, so let's just check. This is just for exercise, right? For example, how about let's try this. U exclusive OR, which means this circuit, H tensor product I. Let me apply it to U2. Okay, what is U2? Just the second vector of the standard basis, right? So this is equal to 1 over square root 2, 1, 0, 1, 0, 0, 1, 0, 1, 0, 1, 0, negative 1, 1, 0, negative 1, 0. Apply to U2, 0, 1, 0, 0. Is that okay? Just by definition. Now, how do you do this? Again, row times column, right? Inner product. Again, which one has effect? You just look at if they have 1, because now I only have 1 and 0. You only have something left if both of them are 1. But they don't have, right? This is kind of orthogonal to this one. right? So the first one is 0. How about the second one? Does it have any overlap? Oh, yeah, it has, right? Because second and fourth are 1. Here, second is 1, right? So fourth will give me 0, but 1 times 1 is 1. So this one is going to give me 1. Right? For those who still not very clear, just remember what I'm doing is 0 times 0 plus 0 times plus 1 times 1 plus 0 times 0 plus 1 times 0. That is this one times this one, what I mean, right? That's how you do matrix multiplication. And you'll be very familiar with this, so don't make mistake on matrix multiplication. How about this one? What do you get? The third one. 1, yeah? And then the last one, what do you get? Yes, because the last one, again, they are orthogonal. Right? So when you're doing multiplication, also try to appreciate that this is actually an inner product of 2 vectors. It's just a bracket, although I stack it in the matrix, right? Start understanding this, and that can help you to construct the algorithm. And what is this state? This is actually just the psi. Definitely is plus, right? And this is also psi, the third one, right? So it doesn't matter. This circuit doesn't matter whether, although I just want to say that, okay, if you plug in the standard basis through this circuit, I will be able to get a Bell state. So there is a way to create a Bell state, yeah. Can you say again? All the column here, Bell state, very good observation. Indeed it is, yeah. Yeah. So he has a very good point, right? So think about this. My standard spaces I only have 1 in one of these locations, either 1 0 0 0, 0 1 0 0 0 0 1 0 0 0 0 1, right? And if I claim that this one will convert this to Bell state, then if, for example, if I have 1 at the second column, is basically you see that you try to only get the second column as the output, right? Because this one times this, I will get this element, then this element, then this element, right? So I claim that this circuit can transform standard basis to Bell state, and my standard bases are in the form of 1 0 0 0 0 1 0 0. Then this column must just be the Bell state, which makes sense. Right, so very good observation. Do you understand what he's saying? Yeah. And then earlier someone asked me, "Is this?" You asked me, "Is it unitary?" Then yeah, now he also pointed out this Bell state, right? And you already gone through the math. They are orthonormal to each other, so everything makes sense. Yeah. Say again.
Still working. That matrix is on my side.
You mean this one become in the front? No, because the problem of matrix is they don't commute. If I call this A, this is B. Usually AB not equal to BA. So you cannot swap that. And then by definition of matrix multiplication is row times column. Right? So you like this one need to follow strictly, okay? Very important. Follow strictly, no mistake on matrix multiplication. Okay, good. So we're done with this, right? But this is an important part in the class. At least you will at the exam. At least you will see a question like ask you to construct the matrix of a quantum circuit. So let's look at the IBM-Q simulation, right, or experiment. This is exactly what we have implemented for the circuit, right? IBMQ has the bottom, when they draw the circuit, bottom is MSB, top is LSB. So if you look at here, let's just make sure, yeah? Hadamard gate, identity gate, control NOT with the control qubit as the MSB, control qubit as the MSB, Hadamard gate, 0. Now I did not add I, right? Because I don't need to. This is a real simulation. I'm not doing matrix multiplication. You can add I, you can skip I, but the physics itself is you do nothing. That is the identity gate already. Okay. I forgot if they have an I. Does it have an I icon in IBMQ for this one? Okay, thank you. Yeah, so you can add I if you want. And this is the matrix we just derived, and someone point out this is actually psi plus, this is phi plus, phi minus, psi plus, psi minus, right? So I applied this, but as we said, by default, the beginning is 0, 0 by default. For all quantum circuit, we want to start with 0, 0, which is just equal to U1, which is equal to 1, 0, 0, 0. Okay? Okay, so if it is 1, 0, 0, let's practice one more time. What is the expected outcome? U times U1 give me, now I call it U, the whole thing, right? The whole circuit is U. 1 over square root 2, 1, 0, 0, 1, 0, 1, 1, 0, 1, 0, 0, negative 1, 0, 1, negative 1, 0 times 1, 0, 0, 0, right? And again, we already say that this is night filtering. Right? This one times this, only this will be left. And then this times this, only the first column will be left, right? So this is just equal to 1 over square root 2, 1, 0, 1, 0, 0, 1. We can write it in cat notation. What is this in cat notation? 0, 0 plus 1, 1. Are you okay? So when I do the measurement, what do I get? I will only get 0, 0, and 1, 1. I should not get 1, 0, and 0, 1 because I don't have that component. And indeed, this simulation doesn't have noise, so it's very clean. I don't have 1, 0, and 1, 1, and 0, 1, right? I don't have these two. Okay. And how do we run the simulation? Do you remember? You try to have many shots. So we did this for 100 times. It turned out to be a little bit less than 500 get 1, 1, and a little bit more than 500 get 0, 0. Which makes sense because if you spin the coin, right, head and tail are supposed to be equal to each other, but you spin 1,000 times, you get 505 times head, 495 times tail. These are just purely statistics. But they are approximately equal to 1/2 probability, right? Why it is 1/2, not 1 over square root 2? Square. This is trivial question, but okay, but you guys cannot make mistake, okay? Any questions? Do you understand now? And that you have something similar in your assignment, right? If you did not do it right, did not interpret it right, please think about it. Let's try one more. Now, what I'm trying to do here, you still have the same circuit. This one is still U. Although they don't align with each other, but doesn't matter, right? It doesn't depend on when you apply it. This is still U. Is it okay? H to the MSB and control NOT gate, right? But I add a NOT gate in front of this LSB. So if I start with 0, 0, then at this point, at this point. What is this? Yeah, very good. One of you say 1, 1, one say 0, 1. Which one is correct? And someone say 1, 0. Okay, first, he say apply to the first qubit, but where is that qubit? MSB or LSB? Yeah, so that depends on what you mean by first and second. That is the confusing part, yeah. But LSB or MSB? Yeah, correct. So this is LSB. So now you say apply to, do you agree apply to only 1 qubit or 2 qubit? 1 qubit, because although the drawing is ugly, but the Q1 did not see anything when it reached this purple line, right? Or when it's right before the gate, yeah? So what is the state here now based on this discussion? 0, 1. Do you all agree? Yeah, because the NOT gate is applied to 0, 1. Okay, so now what we need to do is just look at U times 0, 1, which is U times U2, right? Which is just equal to 1 over square root 2, 1, 0, 0, 1, 0, 1, 1, 0, 1, 0, 0, negative 1, 0, 1, negative 1, 0 times U2, which is this one. And again, we said the multiplication process is nothing. In this one particular, it's just to filter out the second column, right? Again, qubit number 1, you say this one? You think it is, no, sorry, so this is the confusing. This means qubit number 0, not the content. Qubit number 1, qubit number 2. If you have more, you will see qubit number 3, number 4, number 5. Okay, so this one you can discard it. Okay, it's not the, all the quantum circuits start with 0, 0. So both of them are 0. If I make it more explicit, then this is 0, this is 0. Okay, all start with 0. Okay. So let's go back to here. So this one is just to filter out the second row, second column. So I have this. Okay. And again, what is this? This is just the psi plus, right? No. Yeah, this is psi plus, correct. Okay. So I'm done. I can say review or homework assignment, right? But do not think that you need to wait for another few weeks to solve this one. Study it. It will appear in the midterm. You need to understand the quantum circuit. You need to learn how to translate into matrix multiplication, right? And in this process, I've reviewed the bracket notation operation. If you don't understand, you should ask, right? Now, we'll go to a deeper topic. But again, it's also just a review. Now we are talking about control NOT gate, but now the LSB as the control qubit. So what will be the matrix form? Right, so this is also a review, although we use something more complicated. Again, we define the matrix or define a gate by defining how it transforms the basis state, right? So the definition is this: when it is 0, 0, it becomes 0, 0. And we use the same argument as before, but now remember, this one is the control qubit because it's the LSB instead of the MSB. The MSB is the target qubit. Is that okay? Just definition, you need to accept it. Okay, and then why there's no effect? Someone explain to me why 0, 0 is still 0, 0 based on the definition. Huh? Control is 0. When control qubit is 0, you do nothing, right? Okay, good. So then let's continue. What happens if it is 0, 1? Oh, someone say 1, 1. Can you go through the steps why it is 1, 1? Because control is 1, then what do? You apply the NOT gate to the target qubit, right? Because the control is 1, you apply NOT gate to target qubit, it becomes 1, 1. Make sense? The definition is the same as how we define MSB, how we define CNOT gate when MSB was the control. But now LSB is the control, so you look at here, right? So let's continue. What if it is 1, 0? What do we get? Still 1, 0. Why? Other people tell me. Control bit is 0. Do nothing to the target qubit, right? Again, target qubit is the MSB. So finally, what if it is 1, 1? How should it behave? Say again. 0, 1. Because the control qubit is 1, right? Let me say again, right? Control is 1. Control is 1. So apply NOT gate to 0, and then 0 becomes 1 to the target qubit. No, apply NOT gate to what? What? Control qubit is 1. So we apply NOT gate to the target qubit, and target qubit was what? 1. Thank you. Right? Target was 1, right? Apply NOT gate to it, right? So 1 becomes 0, and that's why it is 0, 1. Okay, so that is the control NOT gates with the least significant LSB as the control qubit. So you will see that control NOT gates LSB has this matrix form: 1, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0. Right? Instead of seeing that I have this 1, 1, 1 here, you rather see it as this follow the identity, but except the fourth, second, and fourth are swap, because 0, 1 becomes 1, 1, and 1, 1 becomes 0, 1. Okay? So that is the matrix form. And of course, I need to recall control NOT gate. If you have the MSB as the control qubit, it is 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0. Okay? It would be good to put in your cheat sheet and make sure you understand. Any questions?
To have both.
Both. Yeah. Okay. Be very careful. I have not written the paper yet, so no matter what you ask, it's not any indication of what will be tested.
So we don't have the control.
It depends on, if we, first you need to make sure which one is the MSB, but I definitely would say that, right? And then you look at the control NOT, right? The dot, that would be the control qubit. And then the other is the target, right? Because you see, I applying the NOT gate, right? Based on this, right? Okay, the last thing is that I want to talk about swap gates implementation. This is just an exercise. You don't need to do exclusive OR. It depends on the quantum computing architecture. Some swap gates are easy, like trap ion, you just really swap the ion. But for superconducting qubit, you cannot, because they're solid state. They are already hard-coded on the chip, right? So how do you implement the swap gate? If you have a very high fidelity, very nice exclusive OR gate, control NOT gate, right? Exclusive OR means control NOT, right? I hope you understand now, right? If you have this, then you can use it to implement. So I will just, this is purely an exercise to go through the bracket notation. This is the swap gate, and it is equivalent to this. Control NOT gate here, control NOT gate here, and then one more control NOT gate. And this is the MSB. That's why it's so important to identify which one is MSB. And this is LSB. So, okay, this is given, but we are going to prove it. And proving is very easy because it's quantum computer with 2 qubits. You just need to go through all the basis state because the definition of a quantum gate is just how it transforms the basis state. Okay, so let's prove it. And I hope you can follow. If not, watch the video again. If my input is 0, 0, so I'm going to do this. What should I do? Let me call this 1, 2, 3, 4, right? This is at position 1. My input is 0, 0, and then it becomes 3, 4. Let's do it together as an exercise. What happened at position 2 if input is 0, 0? It's still 0, 0. Why? Because control is 0. And I don't care which one is controlled because both are 0. Right? How about at position 3? What happened? Still 0, 0 because both 0, 0, right? How about at position 4? 0, 0. Is this a behavior of a swap gate? What's the definition of swap gate when the basis is 0, 0? Still 0, 0 because I just swapped them, right? Okay. Okay, then how about the input is 0, 1? What do I get? At second step, what do I get? I'm talking about this circuit second step, not the overall. Zero, 1. Why? Because MSB is control, right? And it is 0. So I apply nothing to the LSB. So it is 0, 1, right? Okay, good. How about the first step? 1, 1. Why? Because the control qubit is what? This time? LSB. Right? When you reach here, it is LSB, the control qubit, and LSB is 1. So you're going to apply the NOT gate to the first qubit. That's why you get 1, 1. Any question? I think this is the most important step. If you understand this, then the rest will be okay. Any questions? How do I know? Because I look at these circuits. Do you see that? I'm talking about 2 to 3. So I'm talking about this gate. And then this is the control qubit because the dot, the intersection is the control qubit, right? This is NOT gate, right? NOT gate is something you apply to. So this is the target. This is the control. Yes, the dot is the control. So LSB is the control. So it means the control is 1. So you need to apply the NOT gate to MSB. So you get 1, 1. Okay? And the way to memorize this is you look at the gates that usually have the action, right? And NOT gate is on MSB. So MSB must be the target qubit. Or the dot is control. That's how we draw it. Okay? Good. Then how about the last step from 3 to 4? What do you get? 1, 0. Because this time, what is the control qubit? MSB. And it is 1, right? Then you apply the NOT gate to LSB. You get 1, 0. And is this the behavior of a swap gate? Yeah? 0, 1 becomes 1, 0. Okay, let's continue. I mean, this exercise, it will be useful. Now I have 1, 0. And after the first quantum gate, what do I get? What? Someone say 1, 1. How about you tell us why? Because the control qubit is MSB, so it is 1. So you apply NOT gate to the LSB, so it becomes 1, 1, right? So how about from 2 to 3? 0, 1. Because the control qubit is LSB, right? And it is 1. So you apply NOT gate to first one, so it's 0, 1. How about the last one? Huh? 0, 1. Because the control qubit is MSB and it's 0, do nothing. 0, 1. Okay. Now maybe you go back. This I think is so. This is again the behavior of swap gate. Go back to just go through this yourself one more time for the last one. Maybe the last 5 minutes. I just want to talk about review. But I have reviewed already. These are all the skills I'm going to test you, right? How to do bracket notation, how to construct a circuit, basic quantum gates, and then some simple thing, right? Okay, so nothing, right? I think at this stage, all those basic things becomes very trivial for you, which is great. You don't need to study again. I hope so, right? You understand how to represent the vector, and you know how to do inner products. Definitely will appear in the midterm, and you should know that you need to do the complex conjugate, how to do complex conjugate for a complex number, right? And when you do measurement, how do you find the probability? It is the magnitude square, but sometimes you can make it as a complex conjugate times the number itself, right? This you all know. Orthonormal basis, what is the definition, right? How do you show that it's orthonormal? You did that in assignment 1. So assignment 2, although maybe simple, but all those are basic concepts you should know very well, right? How do you do inner products? And normalization, how do you normalize a vector? And change basis, this is just, here still just a simple substitution, but we already learned that is something I'm pretty sure will appear also. How to transform a basis, use the transformation matrix, which I will discuss a little bit later. These are the bracket notation equation you should know, right? This is how you normalize a vector. This is not normalized. You just divide it by its magnitude, then it's normalized, right? Polyspin matrices are important and their properties. Spin matrix in arbitrary direction, but more important is what is adjoint matrix, what is Hermitian matrix. You need to know that because I may ask you if the matrix is Hermitian and unitary. And if you don't know the definition, you cannot do it, right? These are just some of the equations. And of course, eigenvalue, we spend a lot of time. You should know how to find the eigenvalue, how to diagonalize a matrix, how to find the eigenvector. It can be very confusing. So be ready to choose a number, because for eigenvector problem, you have infinite number of solutions, right? But you can just choose one and then fix it and then normalize it, like what we did in the exercise. This is the transformation matrix I mentioned. I hope that you know how to construct it. Very important, it will appear, okay? I give you a basis, another basis, how do you transform it? That's to transform a vector, right? And here, of course, it's just the representation. We talk about projection operator, it can appear also. And yeah. This one you can ignore. Tensor product for sure, right? You can ignore those on the left, but I did not cover this year, so I shall copy. But definitely you should know how to do the tensor product for matrix and vectors, right? For sure. And we already reviewed today, right? How to do 1 qubit and 2 qubit gates, there's nothing special. And then we discuss all these gates. You should have it in your cheat sheet. You should know how to apply it, how to transform the matrix from old basis to new basis. This is critical, right? And then just the gates that we have learned. And finally is this Hadamard gate. You can expect that I'm not going to ask you to do those type of lengthy proof, right? That is meaningless. But you should have at least have idea on this equation and some simple things. And that's basically what I will cover, right? Very simple actually, but if you are careless, you can get low grade also. Okay, that's all I have. If you have a question, I will stay.
Is this is posted already, right? This